In this video, we will be discussing how to complete a multi-step energy problem and how to identify when an energy problem requires multiple steps. Our problem asks how much energy is needed to heat a 33.3 gram block of ice at negative 6.89 degrees Celsius to 116 degrees Celsius. In order to answer this question, the first thing that we need to do is identify the substance that they're asking us about. And in this case, our substance is ice or water. Because we know that we are dealing with ice, we know that our melting point for water is going to be 0 degrees Celsius, and our boiling point of water is 100 degrees Celsius. Now that we know and understand what our melting point and boiling point are, we can reread our problem to determine how many steps our energy problem is going to have. Our problem states that we have a block of ice at negative 689 degrees Celsius. That means that our block of ice, or our problem, is going to start somewhere about here on our heating and cooling curve. It doesn't matter where we put our dots so long as we know and understand that it's under 0 degrees Celsius. Our problem also states that the ice is heated to 116 degrees Celsius, which means that our problem is going to end on the gas line of our heating and cooling curve. Again, it doesn't matter exactly where we place our dot so long as we know that it is above 100 degrees Celsius. Now that we know what the starting point and the ending point are for our problem, we can see how many steps our problem is going to be. Since our block of ice starts at negative 6.89 degrees Celsius, we know that we need to do at least one step that involves the equation for heat at Q equals mCp delta T, and we're going to call this our Q1. We also know that our block of ice needs to change from solid to liquid form. So that involves a change in state. So that's going to be our Q2, and we will use the equation Q equals mH. Our block of ice is going to change into a liquid, and then the temperature of that liquid is going to increase. So this will be our Q3, and our equation will be Q equals mCp delta T. Our liquid, after it's been heated, will then be transformed into a gas. So this will be our Q4, again using the equation Q is equal to mH. And then the last part of our problem states that we are going to be heating that gas up to 116 degrees Celsius. So this will be our Q5, and again the equation is going to be mCp delta T. Let's begin with our Q1. Q1 corresponds to the equation mCp delta T, where m is our mass, and according to our problem, our mass is 33.3 grams. The specific heat capacity in this part of our problem is going to be the specific heat capacity for ice, which according to our reference table is 2.05 joules per gram degree Celsius. Our delta T, or our change in temperature, corresponds to our final temperature minus our initial temperature. When we are looking at our change in temperature, we can only use the temperatures that correspond to the part of the graph that we are on. So in this case, our final temperature will end at 0 degrees Celsius. And our initial temperature is negative 6.89 degrees Celsius. If we plug this information into our equation, we have Q1 is equal to 33.3 grams times our specific heat of ice, which is 2.05 joules per gram degree Celsius, and our change in temperature is 6.89 degrees Celsius. If we plug this information into our calculator, we will say 33.3 times 2.05 times 6.89, and we get the number 470.34585. This is a number that we will want to use again. So we're going to use our calculator to store this number by clicking STO and then alpha, and I'm going to save this as the letter V. So our Q1 again is going to be 470.34585, and as a reminder, I stored it as V, and our unit, gram, cancels out with gram, degrees Celsius cancels out with degrees Celsius, to leave us with the unit joule on top. So that is our equation for Q1. Now let's move on to Q2. Q2 corresponds to changing from a solid to a liquid, so that means that we'll use the equation Q is equal to mH. H stands for heat of, and in this case, because we're going from a solid to a liquid, we will be looking at the heat of fusion, so it gets an F. M, again, is 33.3 grams, and according to our reference table, heat of fusion for water corresponds to 334 joules per gram degree Celsius. So Q2 is equal to 33.3 grams times 334 joules per gram degree Celsius. Gram will cancel out with gram. Oh, I'm sorry. There's no degree Celsius here, just joules per gram. So gram will cancel out with gram to leave us with the unit of joule. And if we plug this information into our calculator, we will say 33.3 times 334. Since this is a number that we will want to use again, we are going to store this number, and this time I'm going to use the letter C. So our number is 11122.2, and again I'm storing this as C. Our Q3 is where our temperature increases again. So our equation is Q is equal to mCp delta T. M doesn't change. It is still 33.3 grams. Our specific heat capacity this time is going to be for a liquid because we're on the liquid portion of our cooling curve. And the specific heat capacity for liquid water is 4.18 joules per gram degree Celsius. Our delta T, again, is T final minus T initial. But again, we can only talk about the temperatures for this portion of the graph where we have a liquid. So our final temperature for this portion of the graph is going to be 100 degrees Celsius. And our initial temperature for this portion of our graph is 0 degrees Celsius. So our Q3 is equal to 33.3 grams times 4.18 joules per gram degree Celsius times 100 degrees Celsius. If we plug this information into our calculator, we will say 33.3 times 4.18 times 100. This time we will store this number that we will use again as the letter D. Enter. So our number is 13919.4. Our unit is joules, and we stored this as D. Our Q4 corresponds to changing from a liquid to a gas, so we'll use our equation Q is equal to MH. Because we're talking about going from a liquid to a gas, this corresponds to vaporization. So we will be using the heat of vaporization. Our mass doesn't change. It will be 33.3 grams. And our heat of vaporization, according to our reference table, is 2,260 joules per gram. If we plug this into our calculator, we get 33.3 times 2,260. Since this is a number I know I'm going to need again, I'm going to store this number as the letter E. And our number is 75258. Gram cancels out with gram to leave us with the unit of joule. And I stored this as the letter E. Our Q5 equation is going to be this one, which again is a change in temperature, which means that we use the equation Q is equal to mCp delta T. Our mass doesn't change. Our specific gravity of water when it is in our gas form, according to our reference table, is 2.02 joules per gram degree Celsius. And our change in temperature, our final temperature, is going to be 116 degrees Celsius. And our initial temperature for this portion of the graph only is going to be 100 degrees Celsius. We plug this information into our equation. We would say 33.3 grams times 2.02 joules per gram degree Celsius times 116 minus 100 is 16 degrees Celsius. The answer to this equation is 33.3 times 2.02 times 16. Since we're going to need this number again, I'm going to store this number as the letter F. And this number is 1076.256. Gram cancels out with gram, degrees Celsius cancels out with degrees Celsius, to leave us with the unit of joule. Now we can find the final answer to our question. Since our question was asking us, what is the energy needed for heating a 33.3 gram block of ice at negative 6.89 degrees Celsius to 116 degrees Celsius, since it's asking us about the whole thing, the way that we find our final answer is by finding the total heat energy. And our total heat energy, since it was a 5-step problem, is Q1 plus Q2 plus Q3 plus Q4 plus Q5. So our Q total, if we go over to our calculator, we can say alpha B plus alpha C plus alpha D plus alpha E B, C, D, E plus alpha F, and press enter, we get the number 101,846.2019. In our original problem, we had 3 significant figures for our grams, 3 significant figures for our temperature, and 3 significant figures for our other temperature. So our final answer will also need to have 3 significant figures. If we round this number to 3 significant figures, the correct answer would be 102,000 joules. So this would be our final and complete answer with the correct number of significant figures.